Hello everyone. It's a great pleasure to have Vivian Miranda here today during Thanksgiving. Thanks a lot for accepting our invitation. Vivian is currently an assistant professor at Stony Brook University in the US. She did a PhD in astrophysics at the University of Chicago. Then she was a postdoctoral fellow at the University of Pennsylvania, and finally a postdoc at the University of Arizona. Today, Vivian will present what lies beyond lambda quadrant matter, new physics in an era of cosmological tensions. Please, you can start when you're ready. Thank you.
Hello, everyone. I'm Vivian. I've been an assistant professor for 3 years. Scary, but awesome job. You know, being professor is super fun. So before I start my talk, I will have to say that everything that almost all the results that I'm going to show today, and I'm going to overview some results that I've been thinking relate to problems that I'm thinking about, were led by either my PhD student or my postdoc, Josh Cable. He's in the market, so hire him. He's a really good postdoc. He has my highest recommendation. And I also want to say that ITP is hiring. We hire every year in many areas of theoretical physics. So please apply. The deadline is approaching, but there's still time to apply to ITP. So let's start. So here is an introductory slide about the history of the universe. And for the purpose of this talk, what I need you guys to know, to be with me, is that the fact that the universe, broadly speaking, is divided in 3 phases. An early universe phase, which is between Big Bang and recombination, which is the era where the universe became transparent and the CMB photons start traveling freely. There's an intermediate universe from recombination to reionization, where stars form and the universe ionized for the second time in its history. And there's a late universe from broad reionization to today, where in the second half of the late universe, the universe accelerated for the second time in its history. Each phase is probe type of data, one maybe radio, one 21 centimeters, the other one optical. But the important fact is that physics or new physics in all these phases affect the current expansion and structure, the predictions for the current expansion and structure formation that we see with optical data. And to be more specific, predictions about Hubble constant, S8, and so on. So, and this creates an interesting problem, is that if everything works fine, we just predict the right H0, the right S8. But if it goes wrong, as it seems to be, then there's the question in which redshift sphere, in which phase of the universe we need to alter the physics, or do we need to alter the physics in multiple redshifts at the same time in order to solve or to reconcile the standard model of cosmology with the data? And because cosmology is not an experimental science, we just observe the universe and it comes with everything, at the same time, it's actually not a trivial problem at all to disentangle, to do this reverse engineer where we should alter the standard model of cosmology to, reconcile theory and data in case lambda CDM fails, which seems to be the case. Also, to put everyone in the same background, there are some interesting tensions that we do observe today. The first one is the Hubble tension. This is not the most comprehensive plot, but it's summary. The problem that on blue and triangles, if you're colorblind, you do have the measured value of the Hubble constant by the Schultz collaboration. I'm only including Schultz, but the other always to measure locally the Hubble constant. And in red are predictions from CMB predictions using first not data, then Planck. We have other ones that include SPT and ACT. I'm not including those. Here is just an illustrative plot. And the idea is that if you truly believe that the correct model of cosmology, like the standard model of cosmology, is the cosmology probe by the cosmic microwave background, then the universe we observe seems to be expanding a bit too fast. And this discrepancy whatever is its source seems to be reaching the value of 5 sigma that, you know, can be the threshold for, you know, falsifying the standard model of cosmology. So this is one of the tensions. The second one, which doesn't have the same statistical power, but it's still interesting because it's actually not trivial to fix it, is the problem of S8. S8 is a problem that involves both the amount of cold dark matter in the background and the structure formation. So you can think S8 as if you have two universes with the same amount of cold dark matter in the late universe, like same omega matter, higher S8 is higher linear amplitude around 8 megaparsec. And this plot is complicated, but it seems that that if you again believe that the standard model of cosmology is the model probed by the cosmic microwave background, by the Planck experiment, then the universe we actually see seems to have a little bit less structure than predicted. Or if you fix the amount of structures in two universes, it seems to have less cold dark matter than we predicted. So it doesn't have the same status as H0, but is a problem that is not going away, more or less, in most experiments. And there's a new one, which actually was confirmed by the full shape BAO results from last week, which was interesting, surprising, interesting, that even the background expansion, which seems to be, you know, kind of like, it seems to be like a solved problem. We knew that was close to lambda. It actually might not be. We actually have hints that dark energy is dynamical, and this is the dark energy equation of state in a very specific parameterization of the smooth dark energy with the WNW, the CPO parameterization. It seems that when you combine BAO and CMB and 3 types of supernovas, you have a detection of dark energy, dynamic dark energy. Again, it's not the statistical power of the H0, but it is a problem. And then we do not know if this is just the fact that it's very hard to constrain systematic effects on this stage 4 type of experiments. And if this is the case, if this is the pessimistic view, then we are going to get detections in almost all releases because we're just underestimating the amount of systematics, or we, you know, finally we actually get some interesting physics. I will add this to your judgment, but we just say we do have these tensions. Okay, so this is just like to get everyone on the same page. And now I'm going to overview of a few things I've been thinking about, first related to these DESI results. And ask me questions, you know, please don't panic. And, you know, I have a lot of these little sections. So if I go over time, I can just finish at one section and it's okay. So let's try to talk about like DESI, the BAO results versus supernova, which I think it's an interesting question. Is that, so we have this paper where we found, like after the release of the first DESI results, that if you combine CMB plus BAO, and here in CMB, there's some asterisks here that we are limiting the L modes of the CMB to 1296 because we do not want nonlinear lensing, nonlinear effects on lensing. Lensing also has slightly problem in the TE. So there's this cut, which actually help us understand the clear picture. But within lambda CDM, and here we also include an old data, which the experts do not believe was correct, but we included because if you follow the literature of supernova, something kind of changed from Pantheon to Pantheon Plus, the SY5 Union 3, which are the more modern ones, and that was the value of omega matter. So I'm including Pantheon just to make a contrast. I'm not advocating that Pantheon was the correct one. That's not what the experts believe. But this plots the delta omega, like the difference between what the CMB plus BAO agrees on the left, the DESI results prefer versus the supernova, and you can see that there is a discrepancy in the value of omega matter, the amount of cold dark matter, and this is higher for DESI and Union 3, and that's Y5, sorry. And which is interesting because the experts believe that DS year 5 data is the data that is most homogeneous, that has most systematic control, has the best telescope, you know, so that although we do not talk about this in the data, we have to take this into context. And on the left is just the BO, is just the DESI data. And on the right, we replace two redshift bins in the DESI data around 0.6 and 0.7, where the original paper believed that it was slightly, has some deviations. We replace that by old BOSS DR12, and we still see this discrepancy in the value of omega matter. So we found that interesting. We also, there's other results related to scalar field dynamics, like do we really need a phantom crossing? But for now, I want to emphasize this. There was this deviation in omega matter that was there, and that deviation did not exist for Pentium. So that is an important fact. Again, I'm not advocating the Pentium is correct. I'm just making the statement that something changed in all moderate supernova, the way they all analyzed, such that there was a discrepancy, there was not a discrepancy with the Pentium data, and there was a discrepancy with the new data. And that's why I thought that maybe it would have been interesting for the DESI data to include Pentium just to see that something changed in the supernova. So you can ask, like, what actually the CMB plus DESI observe? And the CMB again here is L less than 1296. And what they observe, you can think of as this principal component here, omega matter minus 0.28 and W naught plus minus 1. And you can see that I put in a way, like I made the coefficients of the principal component such that when the full DESI it's around 0, and then if we replace some of the DESI bins by BOSS, it goes a little bit to the right. But because this posterior is around 0, it tells you that if omega matter preferred by supernova was around 0.28, then W naught will be around minus 1. So that's an indication that the problem of omega matter is related to the detection of W naught WA. It's still not proved, but isn't. And if you and there is something different with the DESI bins on the 0.6 and 0.7. If you replace them by old data, they do shift this posterior to the right, but it does not shift enough that so you see that if you go 0.01, then the omega matter preferred, but that it will be compatible if W naught equals minus 1, will be around 0.2, 0.3. And if you follow the literature, the omega matter preferred by DS is actually 0.35. So it shifts to the right. It doesn't shift enough to make compatible with the supernova. So that is interesting. And if you actually see the triangle plots, I cannot see my own mouse here, but you can see in the omega matter W naught plot that if the CMB plus DESI, they have this degeneracy line, around x equals y, now this general direction, 45 degrees. You can see that it does close a little bit, like there's some two sigma, it's not within the one sigma, so that's interesting. That's really DESI thing, the DESI signal. But it's the supernova that tells you where in this degeneracy line you actually ends up, because that's the principal, that's this degeneracy line is the very orthogonal to the principal component. And then in the fact that the DSY5 wants like a higher omega matter, that shows that this is where it pushes the problem is really far away from W naught equals minus 1 and WA around 0. But you can see that if you just look to the bands, like the blue band, just focus on the blue bands, and then I go to the other one where I do replace the DESI data, all those means to BOSS, you see that there is a change. It goes to the right, and the band in the degeneracy line does not close. So yes, there is a signal from the BO itself. So even if you just do CMB plus DESI, W naught is less favored than what was in the past. But what really pushes the tension to be really high is where you put the supernova, and something changed from Pentium to the modern one. No judgment to because I'm a theorist, I cannot make the judgment which one's correct. I trust now the specialist to say, no, yeah, the Pentium was wrong by X, Y, and Z. Okay, so that's what I want to say about this. So there's other questions around, for example, okay, so given that we do have these interesting results, like the idea is that do we really need to cross the phantom barrier? Because there's a big difference for theorists if you cross the phantom barrier or not. And in this paper, there's interesting fact here that if you go, so this is a plot that on the top are the chi-square of just the supernova data, and on the bottom the chi-square of just the DESI data. And let's go to the left panel, so when you do the Pentium. So for the CMB, and again, CMB is 1296, this is important. And when you combine with Pentium, you can see that both in the DESI part, again, this is not full shape DESI, that's the old DESI from April, if I'm correct. There's like, even in the DAO part, there's nothing here that indicates a preference for dynamical dark energy. But when you combine it with supernova that prefers higher or higher omega matter, in order to readjust, the BAO itself start preferring W0WA, start preferring dynamical dark energy over the other models are scalar field models that do not cross -1. But what you can also say here, from especially in the top one, if you just focus on CMB plus DESI plus DSY5, is that yes, there is a small preference for phantom crossing over the scalar field, but this preference is not strong enough such that priors do not matter. And if you're, this is the Bayesian versus frequentist, there's no judgment here, but if you're Bayesian, if I want to summarize Bayesian in 2 lines, is just do not trust the data blindly. The idea that you put a theoretical prior is that, no, wait, I'm not going to just follow the likelihood, and unless the likelihood really disfavors my model, so like it takes effort for the likelihood to change your prior assumptions. And here it seems to show, at least, and there's a somewhat subjective judgment here, but for me, it seems that the difference in likelihood between normal scalar fields that do not cross the phantom barrier, models that has many theoretical problems, but phantom crossing is hard, it's at least in single field, you might have to multi-field. Again, if you really believe from theoretical reasons that we cannot have phantom crossing, then there's no difference, like enough such that you cannot put a theoretical prior, say, we do not need phantom crossing, and you still have an interesting detection of dynamical dark energy. So that's my statement. But again, it's also interesting when you do Pentium versus DSY5 that the BAO prefer dynamical dark energy over lambda CDM when combined with this, when have to readjust itself to a universe with higher omega matter. If that was not the case, then even the BAO part does not prefer dynamical dark energy. Why? We can discuss that later. So we can ask, like, is the tension in the detection value of omega matter? So, and what that means, like what that exactly means. So we are publishing this paper very soon. The paper is almost done. We're just doing last reviews that, like, are they equivalent? So we written so the first statement is the following. Suppose that the specialists don't believe the systematic exists, although there's some controversies, but suppose there was a systematic that makes the supernova to be exactly like lambda CDM, but with a higher omega matter. So here are mock data where the CMB and BAO has slightly different omega matter, but that's not actually that important. But the supernova, so they are like perfect lambda CDM with omega matter 0.3-ish, but then there's some systematic that makes the supernova to be simulated by a high omega matter. Again, we don't think this will exist. Again, you might disagree with that, but the statement is, if you combine this data, you get a weird detection, a detection of W0WA that looks like exactly what we see in the data. So and that's the statement that if you do combine data that's in tension, you get weird results. But the converse is also true, which I find way more interesting, and we explore a lot in the data, that if the universe was really W0WA, was really some phantom dark energy, in the region, like in the where exactly we see the data, we should expect this difference in supernova versus BAO by the fact that they measure slightly different redshifts, like the dependency is in different redshift bands. So let me clarify. So if the universe is W0WA, but you analyze your data with lambda CDM, you would predict that they would fit different omega matter, and they will fit different omega matter by more or less, at least in the band that we observe in DS, by the same amount that we do actually observe with the data. So that is an interesting statement, and that might tell you that there's no systematics. We just got the wrong model in MCMC, and we do observe a difference in omega matter to compensate the fact that LCDM is a bad model, and that's okay. So we do in the sense that there might not be systematics. It just be that we got a wrong model to start with, which is LCDM background. Yeah. Yes. So this is like I believe the specialist that the Pentile is a poor data. I put it here just the contrast. Something changed, and maybe sometimes when you make a better systematic control, you actually see the effect. Maybe the universe was WNWA all along. We just didn't see it before because all the systematic effects that we got better now. So this requires further analysis, both in the supernova part and the BEO part, to see if the omega matter is real, but it's there. And this role of the supernova is really important in this detection. There's also a higher omega matter, but the universe with a higher omega matter. But there's also the thing like, okay, so let's assume that the universe really has higher omega matter. And that's not just because it's WNWA, and it seems to have a higher omega matter because we just have the wrong model. So that's the case, because that would be the case. But let's assume that, for example, BAO made a mistake, CMB made a mistake, the universe is LCDM and does has a higher omega matter. So that's what that implies to physics in other phases of the universe. So that's what I'm gonna have now. And I'm talking this because before the LCDM, we were working in a paper about early dark energy, where this was a problem. This was a concern. And that's because you can make a combination of data, that's called sound horizon independent data that depends on supernova and do probe early dark energy. So first, what is early dark energy? So I think Vivian Polon is here, so he's the specialist. Please invite him to give a talk about early dark energy. I'm just going to give a very brief result, the summary that is this phase in the universe around redshift 3000, like not that far from matter radiation equality, where you do put a little bit of dark energy, around 10%, but here it can be up to 5. You do not believe it's 25. You just put a little bit of dark energy. Then in the case, in order to shift the sound horizon so that you can explain the H0, because we do believe here that the problem of the H0 has to be solved by changing the early universe, by changing the horizon calibration. That's a very 30-second summary. But the interesting thing that you can use the CMB or data sets that requires a calibration of the sound horizon, that they are sensitive to how the early dark energy change the sound horizon. But you can also use data sets like supernova plus LCDM that does not have an explicit sound horizon there. And the interesting thing is the following. If you take this model of early dark energy, which is the best that we have to explain the H0, and we fit to the CMB, we fit to the data set that depends on the sound horizon, and then without any refitting of the data, we ask what this combination of supernova plus BBN plus lensing talks about, like constrains these models of early dark energy that were fitted to the sound horizon data. If you ask this question, you get this interesting result here. So this result is the H0 here on the x-axis, and the y-axis is how the early dark energy fits this this data set combination that do not have an explicit value of the sound horizon. And there actually was a paper a few days ago from Daisy talk about this. This is a hot topic. Here we did make this assume the EDE, which we think is important. But the important part about this plot is the stars versus the crosses. And the idea is that the value that you assume from omega matter does affect how poor your early dark energy that is fitted by the sound horizon, the CMB data, fits the sound horizon independent data. A universe that has a high omega matter, lambda CDM universe with high omega matter, gives a harder time to early dark energy to fit the sound horizon independent data. And here we just went from Pantheon to Pantheon Plus that has an omega matter of 0.3. It does not even go to the SY5 that has an omega matter of 0.35. And again, we want to have an H naught around 74, you know, and if the universe is like Pantheon, then we could say, oh, early dark energy fits poor, like it fits worse than lambda CD, like non-local energy by a delta chi-square of 3. I can live with that. I don't think that's like that eliminates the model. But if this goes to 8, 10, 12, then you start to have a problem. And that is related to the fact, my earlier slides, that, you know, if you change something like the background expansion of the structure formation in the late universe, that does affect explanations in the other phases of the universe that you use to explain other tensions. So to summarize here, we really hope that the universe is not a lambda CDM with high omega matter. The universe has lower omega matter, and it just have a dynamical dark energy. We did not explain here, we did not explore in this paper what happens if you actually have a dynamical dark energy here. This is something we're gonna do. I cannot see my mouse, but there's more comments here. There's apparently the comments number are going up, so maybe I'm losing.
We can read them at the end, kind of worries.
Okay. So we do not explore in this paper. That's gonna be the next one, because putting early plus late, it takes a lot of time. We require, like, what happens if we do hope that it doesn't have that omega matter for dark energy. There's also the idea that early dark energy does fit poor, like it predicts even higher S8 than lambda CDM, and that cause problems with late time lensing. And you can ask, okay, but now you have a dynamical dark energy, so maybe we can break this. So we actually explored this paper, this possibility with the Pantheon data like 2 years ago. So here is just a plot that shows here the correlation between FED, with the fraction of early dark energy, versus S8, and tells you, like, the more early dark energy you put, the higher you predict S8, and that's a problem. So if you predict that amount of S8, then the lensing data from dark energy survey kids, if they're correct, they will constrain, like they will limit the amount of early dark energy. And we did see for Pantheon data, which is a data set that do not like dynamical dark energy, we did show that even if you put like a very loose 10 parameter parameterization of the late time dark energy equation of state, you do not alleviate the S8 predictions problem from early dark energy. So here is a plot where I combine just the EDE predictions versus different binings of the late time dark energy, and you can see that S8 didn't change. And that's for the Pantheon data. Now we have detection, so the supernova changed a lot from Pantheon to DAS. So it's an interesting question that we want to review, like, you know, if you truly believe that this is correct, and if you truly believe that ED is there, is smooth dark energy, is a CPL dark energy enough, or you have to not only change the background but also put some couplings in the dark energy. Eleonora has many interesting papers about these new types of couplings that really change the structure formation that solves this problem. So that means that early dark energy needs to be modified not only at the background but also at the perturbation level. Not only it needs a different equation of state, but it needs new couplings, it needs sometimes anisotropic stress, and so on. So we need two new physics to solve these two different tensions. In case you truly believe that early dark energy is the only viable solution to H naught and has to be there, means that you believe that the standard model of cosmology is not lambda CDM, is EDE dark energy CDM. And then you have to, and if you believe that, you have to live with the fact that the S8 problem is actually worse than we thought. And can just a WZ solves that? For Pantheon, no, but interesting that the supernova changed it a lot. There's an interesting question that we explore in this paper here. that's like, why stop in WNWA? Like, do we need something more? You know, there's some discussion with Eric Linder, awesome papers about this, which I'm not gonna talk about, but we did some parameterization of WFZ and say, okay, isn't enough. And we did a lot of things in this paper, including some of my favorite dark energy model, which are a WFZ that oscillates. And you could say, why? And I will answer, why not? Kind of interesting, you know, the oscillatory behavior dark energy. I'm not going to talk about this. I mean, from this paper, because I mentioned one interesting result, which I thought was interesting, that so here this plot is a WFZ from this filter, because it's just filtered by the PCAs, but you can see that there's this binning, independent binning of WFZ and DSY5. And I find it amazing, especially the first binning, because there's something in the first binning that the first binning is above -1. It's a small detail that I think is like the cherry on the cake. That if you check, like if you compare this binning, especially the first bin and the one above 0.5 with the dash red line, which is WWA, the DS really likes something like CPL. Nothing more. That's not true for the Pentium Plus. But again, that's where you have to say, if you truly believe that DSY5 is the one that is the purest data, the one that's better control, the one that's actually seeing the truth, then I find it remarkable that if you bin the WFZ like this, it shows something that's very consistent, including the WZ greater than -1 on the first bin, that's remarkably consistent with a WWA. That dude has a phantom crossing. Again, remember my first plot. Phantom crossing is preferred. There's also something here that I should not have done in this paper that actually changed the results a lot, is that we actually used the full Planck here, and that comes with the lensing problem. The lensing axis really pushes for stuff on some phantom behavior, but I think there's a consistency between the two papers, so that pushes the detection further. If you see the Planck 2015, 2018 paper, you see that it's there. But I find it remarkable that DSY5 really wants WWA and nothing more. That's what I want to say. That's, you know, if you want me to talk about the other results of this paper, invite me again. I will be happy to give other talks. So we have all this, and now let's put some physics. Let's try to understand what it means a little bit, and then that's why I want to kind of go further from WWA, like the specific parameterizations of WFZ, to paradigms of cosmic acceleration. The first one is the smooth dark energy. So what is smooth dark energy? We can, but for now we can, because I'm part of the Roman Space Telescope team, we can just appreciate, like, this is the supernova now, the state of the art, more or less. And you can see that the distance residue is around 0.5, but you can bin individually. That's not binning, so it's like a 0.1 if you bin. And you can see that it goes to 1, and there's not a lot of supernova above 1. I love supernova between 1 and 3. Why? Because if you just think in scalar fields, you construct scalar fields so that the dynamical attractor, the final dynamical attractor, is something close to lambda. Assuming that lambda was correct. Like the theorists can tweak the dynamic attractors to look like the data. What they cannot tweak is the transition behavior between the saddle point of matter and the final attractor. The behavior between two attractors, even if all models have similar attractors, that is model dependent. So I actually think that between 1 and 3, is where you can see the models change, because that's where theoretical physicists do not have a lot of control. That's not, they usually can only tweak the parameters to fix the attractors, not the behavior between the attractors. But Roman will go much better. This is some of the Roman. I was part of this paper, like the simulation about Roman supernova. Different strategy. Does not matter a lot what the strategies are, but you can see that's much smaller. So one thing that the supernova can tell alone, does not depend on the data, is that is the universe compatible with cosmological constant? Yes or no? Let's assume no. So that's a question that supernova can answer. But let's assume that's no, it's not. Then what? Like, how do we put some physics in dark energy here? So let's assume now is okay. So we broke lambda, it's not lambda, and now we want to put physics. We want to talk to particle physics and say, look, let's create a model of dark energy through physics that create a new standard model where particle physics will be happy and phenomenologists like me will be happy. Like, what are the physical assumptions that you're gonna put? And and to prove these physical assumptions, we need both expansion and structure formation. So let's look like what is the simplest model of dark energy you can create. And I believe that again, this is subjective, but I believe that they call the smooth paradigm of cosmic acceleration that was first, I would never say the first, but that was explored by Wayne and Dragon in 2009, which assumes the four things, which I think it's pretty reasonable for a simple paradigm, which is assumes GR is correct, assumes that there's no explicit coupling between dark energy and dark matter, no explicit coupling between dark energy and baryons, and that means it's just a minimal coupling, it's just the coupling of the square root of minus g, that gravity couples everything to everything by this minimal coupling. And there's no clustering, like the sound speed is 1, there's no clustering on scales much smaller than the Hubble horizon. That creates those physical assumptions. First, it creates the smooth paradigm of cosmic acceleration, and here you have all models in the left that are compatible with this paradigm. You have the lambda CDM, flatter curved, you can have early dark energy, not early dark energy, you can have quintessence or K-essence, which means like phantom crossing, not phantom crossing, multi-field, but this is what the compatible with this. At least for single field, multi-field is interesting, but I think even with multi-field, it's within this regime. And then you can ask the question: if I don't want to falsify a specific parameterization, I want to falsify the entire paradigm. I want to prove that these 4 hypotheses are incompatible with each other. How do I do it? And to do that, you have to use structure formation, because this is the matter-power spectrum, which is the Fourier transform of the 2-point correlation functions of dark matter particles. It has a component from inflation, which is early universe blue. It has a transfer function that has physics from the intermediate and early universe. But it has this change that is scale independent, this Gale factor. And the interesting thing is that dark energy in the smooth paradigm only affects the scale independent part, and it affects through an ordinary differential equation that is completely specified, a solution that's completely specified by the background expansion. That means that the background expansion, once fix how the growth factor behaves. So there's a consistency between the background and the structure formation on linear scales that, if broken, falsify not only a particular parameterization, but falsifies the entire paradigm. And if that falsifies, that's interesting, because if some of those 4 hypotheses are false, that is pretty interesting. Now, which one will be false, I don't know, but one of them will have to be false, and that is kind of remarkable. That is like game-changing news. So you're gonna need both, and this is something that is being in my mind a lot, that how to falsify this paradigm. You can try to do some model, it's not exactly model independent, but instead of going model by model scalar field, you can do some tests that it's still parameterized tests, but it's not a perfect test, but it starts to probe this type of things. And one is the growth geometry split, where you take the omega matter that goes into the background Hubble function and goes to the Hubble function that enters in the growth factor, and you split them and say they are independent. This consistent do not exist anymore. You have a geometry omega matter and a growth omega matter, or a geometry W naught and a growth W naught, and you see if the data shows that they are the same. And you can see that if you change the growth, you change the matter-power spectrum, which is the dashed lines, in a k-independent way in the linear regime. Of course, in the nonlinear regime, you do have some k dependency, which is, and how you do the nonlinear regime, that's an interesting question. We can talk later, but this is, and you can see that, if some of the things that the recleansing are seeing bleeds into this test. And another thing that I like, that this test is actually pretty sensitive to weird models. And here, weird is just not usual. There's no judgment here. For example, this is a model, I put it here as the true model, a model where dark energy has anisotropic stresses, which do break. It does create clustering. And you can see that you got geometry omega matter and growth omega matter that are very different from each other. So it is a sensitive test. How sensitive? I don't know. Like, one thing that I would like to do is take like some of the models that Eleonora is investigating and see how they map into this growth geometry and growth panels, create some predictions that I think that would be interesting, like where they lie in this independent task, because that is simpler for collaborations to do than running lots of different models, and there's many different types of coupling. Just an idea. Okay. And then one of the things, if you've been following, I know I've been 40 minutes, but like I have more slides, so, I don't know. But can I just continue a little bit?
Okay. Yeah, go. Mm-hmm.
So you can, if you follow DS, you can see that there's a problem. Like, there's an inconsistency between cosmic shear, the autocorrelation function of CMB lensing, of DAS lensing, or of galaxy lensing, and the galaxy clustering, the autocorrelation function of clustering of galaxies. And there's an inconsistency between that in the red magic DS, and that's when I combine the chi plus chi minus plus W theta, and you can see that it bleeds into these tests. So I would like to have all these combinations of lensing data to predict the same consistent delta omega matter, consistent difference between geometry and growth, but it's there. Like, it's sensitive to systematics, it's sensitive to models. So this is something that I think is continue worth exploring. And there's other ways to try to break the consistency between growth and geometry. I think that's worth exploring. Booth, for example, has an interesting paper recently with that also breaks that. That's, I think, the interesting line of research. And then here I would like to talk, there's two things I would like to talk more. One is, like, this is really going to my mind, which is the following. There is no cosmology. I will make a hot statement. Okay, prepare yourself, brace yourselves. Hot, it's on YouTube. I either get praise or cancel or both. So there is no cosmology, comparative cosmology in the next years without nonlinear scales. We do have a little bit because LSST will have more area, so that's more linear scales. But for example, Roman does not have that much area. So, and the CMB is damping tail. That's all nonlinear scales. There's no linear lensing. Even in Planck data, I see a lot of papers that refer that if you use the full Planck data, there is no linear lensing there. That makes a delta chi-square of 2 or 3. If you do not put the nonlinear scales, that is a systematic there. So even Planck, full Planck, it's still sensitive to nonlinear scale. There's no cosmology nonlinear scale. And that is a huge problem, or challenge, or opportunity. So how do we do this? Because, like, we cannot run any-body simulations for all the models you want. So I've been exploring two types of ways of doing it. One is from this COLA, this quasi-any-body. The idea is that you do Lagrange perturbation theory in the large scale of your box, such that the numerical derivatives only have to compute the deviation from the Lagrange perturbation theory, and that allows you to have less time steps, and it decreases the computational effort for by a factor of 100, which is good. The problem is that that's a not perfect solution. So a lot of simulators showed this type of plot, and they thought it was okay, So the reason of this paper where I work with Koyama and Hans Wind is that I said, I look to this plot, they look to this plot and say, oh, it's okay. I look to this plot and say, that's not okay. Lensing in the stage 4 will be sensitive to a few percent, even if you make scale cuts up to 1. And I showed them, so we showed them using elasticity Y1 that you have to, that if you do, they usually combine like data from high definition lambda CDM seams with these colas, and if you're close enough to these high definition anchors, you are fine. But we show that those small percent difference can actually correspond to huge biases. So not good. And in this paper, we did fix those biases to a new way to merge lambda CDM high definition simulations with COLA only using to extend the parameter space to other models. It actually worked really well. I can give you a whole talk about this, but just so that this is hard. And this type of errors is actually very close to the type of errors that you got from effective field theories, which also worries me a little bit. But the second way is from effective field theory of large scale structure, where you use you say that your UV completion of that you cannot model bleeds into these parameters, sound speed parameters that you have fit from the data. This is something that I'm also thinking about, like, but because you have so many parameters, that is that useful? Will that in practice allow us to go further? You know, who will win, like the data or the number of parameters? Do we have to put bispectral? So I'm starting to think about this from a practical point of view, because most of the calculations has already been done by the field theorists. And we are trying for the first time to do, not the first time, but to do an elasticity, like stage 4 and also DS, 2-loop calculation on the optical lensing. And the problem with that, of optical lens, is that these coefficients that encapsulates the UV material that you do not know, they are redshift dependent. That is the whole shenanigans, because the BAO from DESI, because it's spectroscopic and clustering, you can put very fine redshift bins such that these coefficients are constant. That's not true for lensing. Optical lensing has a huge kernel like CMB lensing, so you need to model the redshift dependence of this, and this introduces more parameters. So this is hard. How do you gonna do this? Even if you can calculate the loop, the P0, P1, and P2 for coupled dark energy, for example, how you're gonna model redshift dependence of these coefficients? I think this is the key question that I'm not seeing a lot of people thinking about. So we are gonna think about in this paper that is gonna be published soon. But in principle, like, if you can do that, the EFT, the 2-loop, is interesting. It does allow you to go to K with a few percent. There's some oscillations here in the fractional difference that comes from the fact that there's no RR resummation or calculation yet. But this is the second part. So we need this. So and how to expand quasi-antibody or EFT to a much broader range of dark energy. I think this is where phenomenologists and theorists can make a huge contribution, which I'm not seeing happening a lot in the literature. You know, and this is a really, really, really hard problem. So we're trying to do this. Here we're going to do just from lambda CDM, just to show that EFT works. So we are being very conservative here. And this is the problem that I'm showing lensing. The window function W is really broad, so you really need to model the redshift dependence. There are many ways to model redshift dependence of these Wilson coefficients. We can do parametrizations like we're doing here. That's not perfect. You can do some splining, so we're exploring all that, but that creates more parameters. So the question is how you model nonlinear scales for beyond lambda CDM or beyond smooth dark energy in a way that you actually get more information because you do not have that many new parameters, or you get prediction for pulse spectrum and bispectrum such that they combined give more information than the number of parameters. I think that this is the key question for beyond smooth dark energy research in the next 10 years. And then if we do not solve that question, we do not progress. We're not going to make any progress. The new data is not going to be useful. Except from, it's going to be a little bit useful because Rubin has more sky than DS, but it's not going to be that much more useful. Like we need to solve this problem. And also there's also the question that, which is going to take 5 more minutes, that there's also the interesting thing that we have more parameters. These calculations are hard. Like this 2-loop calculation takes like 10 minutes per cosmology. How are you going to run chains? How are you going to run, do any calculations? Or if you're a Bayesian, you like fancy integrals that takes forever to run, such that you can do this. And for me, that comes from Brazil. Brazil does not have that many high-performance computing resources. How to do it in a way that allows broader range of researchers to do this, not only people that have access to fancy supercomputers, and that's especially true because there are geopolitical tensions that are making many countries to not have access to the types of GPUs that people are using to accelerate some of the computations that I see. So this is where machine learning emulators comes. I can stop here if you want to say, oh, please stop here, or I can do a little bit more. It's really your call. I make these breaks to give you the flexibility, and I'm totally fine, and I can do this, but I can just say that this is something that I'm been really thinking. It's something that I'm going to put in, that I published 2 papers this year, and I'm going to publish a few more, how to do this in a way that but I can stop here and just go to the last slide if you want, because you guys, you know, that
I think you can do 2 slides, no worries, okay? Yeah. I'm happy to listen to you, so you can, there is no reason to skip the slides, yeah?
Okay, so good. Who needs a break? Who needs to eat? I don't. I'm okay. I get some nice breakfast before this talk. So okay. So what is an emulator? What is a machine learning emulator? There's the question about, oh, machine learning can detect new physics, but how do we explain, how to predict? That is not a problem for this type of things that I'm going to explain. This is like this. We know how to compute the physics. We understand the physics. It's just too slow. So this is the problem I'm facing. So there's no question, oh, it's like the Hitchhike Guide of Galaxy that machine learning say the answer for cosmological constant is 42. What that means, that's not a problem for us here. So machine learning emulators is just a map from cosmological parameters to the data vector of your experiment, whatever they are. We did for 3x2. We're also doing for CMB now. And in case here is going to be real space correlation functions. And this has been done many times before, but it's hard to model real space. And the way it's been done before, even from myself a few years ago, is that if you just use like normal machine learning designs, you cannot model the entire parameter space with precision. So what they do is some kind of iterative approach that models correctly the data vectors in the region where you believe that the data will face. And you can see here that like the two posterior will be black, and you do some iterations here such that the machine learning becomes good black. And you can see from the shades that if you go far away from this, you get a bad result. And that is hard because what you want is to give an emulator that people say, look, you can inject new physics, see shifts, do whatever, and you know, and the emulator will be precise, not only in a large volume from space, and with other metrics that I'm going to talk about. And this is where we believe that the designs using attention mechanisms really shines. That's something that really do something that was not true before. So we designed this machine learning. So the first part here is this 2 dense layer was what used before. It's called RAS MLP, a RASNet type of. So we put on top of those some attention, some transformer blocks. Transformer blocks are the blocks of ChatGPT. They're used for ChatGPT. And in these 3 papers, we're doing this for both correlation. In this last paper, we're going to do a lot about CMB, cosmic variance CMB. And we show that you can, if by doing better designs, by doing more modern designs, you know, like this, or like 1D CNNs, which we're going to explore in this 3rd paper, you can expand the parameter space where this posterior, these machine learnings are available by an enormous amount. So here is the MCMC chain, similar to what you see before, the red ones. And these dashed lines are a new training, are a new volume where the machine learning works. And these two dots are 20 sigma shifts on sigma 8. And this was a second paper with a temperature of 512. The temperature is a parameter that you can broaden the covariance. We now can do temperature of 2056 with further optimizations. So because, and this will be interesting because now the experiments can just give you a machine learning emulator. Instead of giving a chain that you have to import and sampling for your model, they can just give you an emulator, say, look, if you want to redo our results, here's an emulator, and you can combine with your you can put new data, you can combine, and it does not take a lot of training to get this to get those large volumes. So this is what a better machine learning design can give you. But also, and you can see here, so there's like no retraining with a single emulator. You can widely shift, and it takes, you don't have to retrain. You can run those in a laptop. They are incredibly fast. We were able to even get evidence calculations in a laptop with these wild shifts. And then this is the other part that is a complicated part that was not shown before. Every machine learning paper that I've seen so far, they tell you the median of the loss when they tell machine learning works. But if you want to do this in the data, you have to look the tails. Because if you look to the DS and say like, well, yes, if you make a theoretical approximation, a machine learning is a theoretical approximation, what is the level of the delta chi-square precision you need so that you don't have to do important sampling? It's an arbitrary choice, and they will say, at least in the year 3, they say the error cannot be greater than 0.2. So you need to tell you not only what is the median of your loss, which are the dashed lines, but also what is the fraction in the tails where you are above the thresholds that the collaboration wants, and that's the solid lines. And we are showing this in this tree that this more and more the designs that not only allows to get lower mean, but they're very like they are insanely better than the previous designs on the tails, because these are very non-Gaussian distributions. So you can actually get, so for us, we made this arbitrary choice that a machine learning to work, to be safe, has to be applicable in a large volume, and it has to predict the fraction of testing points above 0.2 to be below 10%. And that is much more strict than everything that I've seen so far. And that's where, if you do modern designs, you're really going to see a shift that will make the collaborations to finally be comfortable to use machine learning on data. And this is, we have a 3-part paper. We're going to put the last one out. We show that this is true from CMB, and this uniform sampling is a uniform sampling in a semi-large box, and it shows that like machine learning can give you this level of accuracy with better designs, such that you can use on real data and not have worry about, and the fact that you have to take into account the tails of distribution if you want to respect the goodness of fit test, not only bias in the MCMC test. Okay, I finished. Sorry for going delay. And I will just end from the fact that why do I talk about a lot of things? I talk about things because I truly believe that we're kind of, cosmology is like a game of chess. This is a very famous game where a Brazilian GM actually checkmate Magnus Carlsen, which is insanely hard to happen. And here, like, if you want really to understand what learning cosmology, we need to get to attack the astronomical cosmology through many lenses, so that you do not have loopholes. We have to have this like topological view, and to understand like from 21 centimeters from H naught to, can we change inflation, to put them together, because changes in the multiple areas of the universe do affect H naught and SH, do obfuscate our interpretation of like what is the physics you need to do to solve these tensions. So like uniform, like premature attacks to a single line fails in chess and fails here. So that's how it's over and over again. I see papers that do one attack, which is important, but to get like understanding, we're gonna have to do these multiple attacks, and this is impossible to do in a small group. That's why groups need to collaborate. That's why that is the real justification why we need so many different data sets. Why do we need 2 lensings with like Raman and Robin, 2 CMBs? Why do we need 3 supernovas? Because we need to get this overall view from different redshifts. Now we got an interesting redshift range from 21 centimeters from different systematics, so that we can get this like this global attack. Otherwise, we will always be confused. And it's especially true because the systematic will be so severe in the next few years that the pessimistic view, which I'm not saying is my view, is that we will not be able to control the systematics, but we think we will be able to control the systematics, and that will create detections everywhere. We're going to have new detections of new physics in every data, in every release, just because we never control the systematics, and the systematics are like will be so important. We're so deep in systematic limited that even small inaccuracies in the systematic modeling creates a detection. So people say, oh, we're in the era of cosmological precision. I thought no, we're in the era of cosmological confusion. If that pessimistic view holds, which does it hold? I don't know, but that's one view, and the fact that the first release of DESI reached the first stage 4 release, the spectroscopic, which is way better, we think that's way better controlled than photometric, created detection. It is a warning sign if the detection turned out to be systematic. There's the positive view that we are finally be able to get a more interesting model, but we have to be aware of this pessimistic view. And if that pessimistic view holds, we are going to need this like topological. I use topological here in a very loosely manner, like more chess, not mathematics, but that in order to get an understanding of all this detections that are going to pop up everywhere. And that and I think that is way more interesting. Like if cosmology in this decade was just to measure W naught, WA, or W naught with 1% accuracy, that would be very boring. The fact that we have this confusion and we need all these angles of attack is, I think, what makes cosmology super fun now. And I talk way too much. Let's do some questions. Thank you.
Thank you so much for the very great talk. Erin, you have a question?
Hey, Vivian, thanks for the talk. Yeah, okay, I have a number of points actually. Right. So first of all, let's start with Omega M, right? In the Lambda CDM, Omega M is essentially the backbone of the model, right? Because basically that's the thing, it describes the background, and it basically describes it between Z equals 0 and relatively high Z before you get into radiation. And essentially, it's billions of years of evolution at the background level, at the level of the equations of motion, the Einstein equations. So it's really, really important to understand if Omega M is a constant or not. And your talk did get into that, right? So that's the first comment. So it's a very good thing to look at. The second comment is this. Suppose we have BAO and supernovae, and they're in the same redshift range, which is more or less what we've got with DESI and say, the supernovae samples. If independently we fitted the BAO to Lambda CDM, the baseline model, and we fitted the supernovae to the baseline model, and we found Omega M is 0.3, the question to you is, would you expect a dynamical dark energy signal in a W0 WA CDM model?
Wait, let's see. So
that's just a yes or no question, and then I'm going to move on.
So let me just rephrase to see if I understand the question well.
The question is this: if I fit BAO, let's say DESI BAO, and I get 0.3, for Omega M, and then I fit a supernovae sample and I get 0.3, it could be Pantheon, it could be something else. Would you expect to see, if I combined them and fitted the W0 WA CDM model, CPL, would you expect to see a deviation from Lambda CDM?
No. I will
exactly. So this is one of the points you were trying to make, right? So it's just interesting, it's good to think about this thing. It basically tells you that what DESI is seeing when it combines supernovae, BAO, and CMB, there are discrepancies in Omega M in the baseline model that are then getting absorbed into a more complex model, and then these parameters
but-
W0
but-
and WA
But the
deviate,
question
right?
is the deviation a natural consequence that the fact the universe is truly dynamic or dark energy, or that is Stefan? I can never pronounce his name. Can someone teach Stefan George? He's gonna
If
send
that's yeah, George. Okay, so
George. He's gonna send me an angry mail. I hope he was like, Vivian, you don't know how to pronounce my name. I apologize.
right, but here's a concern.
Like,
Here's a concern I have, Vivian.
I
right?
don't know. Like, but let me just finish this sentence. Like, is there a systematic that look like an omega meta deviation, or omega meta is a natural consequence from the different background? I don't know.
Right, but here's another concern I have. Suppose BAO and supernovae are probing exactly the same redshift ranges in any model you choose, and they disagree on cosmological parameters. Let's say lambda CDM, you fit the lambda CDM model, and you know that BAO and supernovae are probing exactly the same redshift ranges or overlapping redshift ranges. If they disagree, there's a serious problem there. It means that ultimately
I don't think it's possible for supernova and BAO to probe the same redshift range. Let me explain why. BAO is like one redshift bin. There's the RS things. Let's assume the RS is fixed. That's a huge thing that I'm assuming. It's like the actual distance to that bin is X. Supernova is not like that. Supernova is always the comparison between high Z and low Z. That's why that's because it's this comparison.
No. I mean, let's just take.
Well, let me just finish the sentence. That is why supernova is not sensitive to H naught, because it's always a relative. So because you always have two redshifts, minimum you have two redshifts in the game. I don't think you can ever say, oh, supernova only measures redshift half and BO only measures redshift half. Therefore, they have to give the same omega. No, because they always have two redshifts in game. So in this sense, I don't think there's no equivalence between them. It's not like doesn't make
right. Okay, but okay, let's leave that aside for the moment, and let me just make two more comments before because we'll get sidetracked.
Miguel is the author of my first paper. Miguel, thank you for coming. Like I have Miguel.
Vivian, sorry, can I just finish these 2 points? Like here it is. DES has a 2 sigma deviation from lambda CDM in the W0 WA CDM model, right? That's a result from the DES paper.
The supernova one, yes.
Right. Now, if we then take the same sample and bin it and fit it to the lambda CDM model, would you expect omega m to be a constant across that sample? Because if it's a constant across the sample, you would find a contradiction. You'd have a 2 sigma deviation from lambda CDM in DES in this more complex model, but then you wouldn't see it when you bin the data.
I think so. I think so. I think so. I think I agree with you that you don't expect.
Right.
Yeah.
So basically, we've already done that analysis, and we've shown that omega m increases with effective redshift in DES. And this brings me back to work we started in 2022, where we showed the same signal was there in Pantheon at very low significance. Then we went to Pantheon Plus, the significance increased, that was 2023, and now we're at DES. And our statements throughout have always been that omega m is not a constant across supernovae samples.
Yeah, and that could be just because, like,
and this was the early part of your talk, right?
Yeah, seems you have to do the analysis exactly the way you did it, but I believe that it seems consistent to what you're saying.
So if we look at what DESI are claiming or what's in the air at the moment, people are saying, well, okay, there's differences between data sets, but it's also possible that those differences are there in the model across those data sets.
Yeah, I think so. Yeah.
Nobody's making this statement yet, though. We made it in 2022. We started making it in 2022. It's still not gone mainstream, right? But I mean, all the ideas to put it together.
Because I think everyone was waiting for the full shape. Everyone thought, oh, that's a fluke. The full shape is gonna put things back to where it's supposed to be. Well, it didn't. So now I think this is really hot. But yeah.
Right. The full shape is, you mean the recent results?
Yeah.
Yeah, they look all very. The only interesting part of that is sigma 8 seems to show some scatter in it. Which It's a small thing. All right, over to Miguel. Thanks very much.
Miguel, it's always a pleasure to hear from you.
Hi, no, quick question, so I don't run too late. So Vivian, in the end of the talk, you're talking about doing, two-loop power spectrum and also lensing. And you're talking about all the bias parameters, right? So that's always the headache is the nuisance parameters, the counter terms, all these things, right? So at some point you were saying you cannot then use them in different ratio beams because lensing correlated beams, but don't you agree that the most model independent thing you can do, the most let's say agnostic thing is to leave this completely free in each ratio beam instead of trying to make, try to guess what they look like as a function of redshift?
Well, so here's the thing. Yes, but you have to do this in some. You cannot just because it's a continuum, and you have different redshift, and it's a continuum. So you cannot just fit like this and make this because we do not know if this has like breaks, if that affects. So you could, and we do this like we could say. We find that this is a really good parameterization lambda CDM, and you can say the two Wilson coefficients is this, and you can put some B splines on top of it that allows the curves to, in a way that is kind of continuous and not like high frequency, to go up and down, which is, I think, is the spirit of what you're saying. The problem is that the number of parameters explode because here you already have 6. You have stochastic quad, CS1, CS4, CS2, and all of them are free functions. You do not win any information from going to this case where the EFT tell. And it's worse because Ivanov shows that if you have that many parameters and if you just put flat priors, you're gonna have volume effects that are actually gonna bias your result. So yes,
I appreciate volume effects, but I think that's it's the most let's say agnostic thing to do. And then you have to worry about these things. You're right, but otherwise you're making assumptions, right? That again, someone can say I don't trust these assumptions, and you go in circles a bit.
Yeah, but it's not so. I think it's not so. I think it's like an onion. There's always like going the most agnostic thing always will give you constraints that are loose, and it's very hard to make to get any detection. So you need the more like thinking by Bayesian sense. You need to make the most stringent prior ever. In terms of number of parameters to get a detection. And if you get a detection or you get some deviation, then you can legitimate question. Okay, is this because my theoretical assumptions are wrong? And how far, and then there's a theoretical question is like how much these Wilson coefficients deviates from this parameterized formula in model X, Y, and Z. But this is something we can answer with simulations, and we don't need 1,000 of them. So I think that's always true. Like you can always go the most general ever, difficult to have any meaningful constraints. Most constrained one, you can get a detection, and then you, like an onion, you're gonna peel each one of those to see, okay, is this a real detection or my sound, I like to tell sound speed, but my Wilson coefficient has the wrong redshift evolution. And this is something we can answer with simulation. So this is something we explore, like there's a balance here that we have to have in these EFTs in order for them. Because not only we need this balance, I think we're going to need higher order points, because the one thing that's pretty nice that once the power spectrum fixes this Wilson coefficients, there's some interesting predictions for the bispectrum. So if you combine them, maybe you have enough data to be very model agnostic. But we are trying here to explore in this paper these different extremes. That's why in our paper, we're going to have like a conservative and aggressive model. The conservative is exactly what you're saying, and the aggressive is this, at least for lambda CDM. And then I'm very interested, and what I think is a really hard calculation to see how in the model, some of the models that Leonora explores in coupled dark energy, these changes. And it changes, and you can have a coupling on the energy, a coupling the velocity, how them, and that will allow change not only the P0, P1, and P quad, which are just complicated integrals. And I think if you make parameterized versions of the transfer function that approximate the coupled dark energy, you can compute those integrals fairly like mathematical. It's not the one, but then also how these Wilson coefficients do change, how you make in a way that you can get actually meaningful constraints from this extra decade, because EFT gives you an extra decade. And actually, to go to one, actually you're gonna need the 3 loop. That's because even though the 2 loop fixes well, the 3 loops is pretty important. So to go too close to 1, like 0.8, you need 3 loops. So that's actually 2 more Wilson coefficients. How to do it then in a way that you actually get meaningful constraints? That is what I'm concerned about. And that is this balance that you said precisely. Being agnostic, it's like EFT of dark energy. You got the Lagrangian, the symmetries, crazy, beautiful, very difficult to get any meaningful results because there's just 5 functions. We will not be able to constrain 5 functions even with stage 4 data. Another hot take that can be canceled, but that is, and how you do that, I do not know.
Okay,
and that's why
thanks, Vivian. Yeah, I understand. Thank you.
Yeah, and it's always a pleasure to hear and see you.
Yeah, Sayantan.
Okay, I'll just shoot a very small question, maybe from the theoretical point of view, because I work on theory. So, as far first of all, a great talk. So, as far I understand that you actually mentioned that whether data prefers the quintessence or the phantom crossing, and as you said that, I mean, if you take the phantom crossing, or it makes the S8 much worse. So, I'm asking that in the string theory or the brain dynamics, etc., what in the say called the string theorists actually propose. So, they are working too much on the DBI field like Neil Turok, etc. Also like the other quintum model, which has both quintessence as well as, I mean, the kinetic term can go switch to the plus and minus, etc. So I'm just asking that even though these are very exotic examples for late time behavior, so do you see any type of this exotic theoretical, say, brain motivated k-essence type of field could resolve this from the theoretical point? So I just wanted to ask your opinion. Also, thank you.
I think it's an excellent question. I'm always open to parameterization that comes from string theory. Maybe I do not say that the phantom makes the S8 worse. What I said is that big enough such that prior from theories like you, like if you say to me, Vivian, we really cannot have phantom crossing. It's pathological. I think that delta chi-squared there, it's not big enough so that this type of prior consideration from theory cannot be taken into a Bayesian to say, look, what the universe actually is non-phantom crossing quintessence or this modified quintessence from brains. That is the true universe, and that's what we're seeing. That's my statement. The delta chi-square is not at that level. Like the significance for the there is a preference. It's not it's not strong enough, and Bayesian for me, it's a balance between what the data wants and what the theory wants, and that for me, Bayesian is do not follow the data blindly. If you have very strong theoretical reasons to do so, unless the data really pushes you throughout that, and my point is that it doesn't push you that strong enough to say it has to have a phantom crossing, even though it's preferred. So, and then then it comes to theories like you to say if phantom crossing is really pathological or not, and that goes a little bit above my pay grade. But I'm open to all types of possibilities.
Yeah, thank you very much. Actually, I was interested in this because of the latest string theory, the Swamplight, etc., puts a very tight bound on the potential, right? I mean, from purely theoretical point of view, like the string theories, etc. So that's what I was wondering, that maybe if there is a synergy between observation and the theoretical front. Yeah, thank you very much again for this amazing talk.
I think we can thank Vivian again. Thank you so much for a very great talk.